Hello everyone, I am Srinivas of ECA department, roll number 611947. Today we are going to learn about stability and causality of digital systems. What is stability and how do we define it? Let us see about stability. A system is said to be stable if the system produces a bounded output for a given bounded input. In the previous slide, bounded means finite in amplitude. For a stable system, the output should be finite for finite input at every instant of time. In this slide, we see the conditions for a signal to be bounded. A signal is said to be bounded if there is a finite value v greater than 0 such that the signal magnitude never exceeds v. That is, for a discrete time signal, the magnitude of y of n must be less than or equal to b for all n belongs to integers. Whereas for a continuous time signal, the magnitude of y of t must be less than or equal to b for all t belongs to r. Here r is a real number. Let us see the time domain condition for linear time invariant systems. For a continuous linear time invariant system, the condition for stability is that the impulse response h of t be absolutely integrable. That means integration of minus infinity to plus infinity, magnitude of h of t dt must be less than infinity. Let us see the time domain condition for discrete time linear time invariant system. For a discrete time linear time invariant system, the condition for stability is that the impulse response h of n be absolutely summable. That means summation of magnitude of h of n from minus infinity to plus infinity must be less than infinity. In this slide, we see frequency domain condition for linear time invariant systems. For a continuous time system, the condition for stability is that the region of convergence of the Laplace transform includes the imaginary axis. When the system is casual, the ROC is the open region to the right of a vertical line whose abscissa curve is the pole that has the greatest real part of any pole in the system. The real part of the largest pole defining the ROC is called abscissa curve of convergence. Therefore, all the poles of the system must be in the strict left half of the S-plane for stability. Now we see the mathematical stability condition that is derived from the time domain conditions. For a time domain condition to be stable, we know that integration of minus infinity to plus infinity mod of h of t dt must be less than infinity. In this slide, we can write integration of minus infinity to plus infinity mod of h of t dt as integration of minus infinity to plus infinity mod of h of t into mod of e power of j omega t dt as mod of e power of j minus j omega t is equal to 1. This can be finally written as integration of minus infinity to plus infinity mod of h of t into e power of sigma plus j omega into whole to the power of minus t dt. Here we can write sigma plus j omega as s. Therefore, finally we get the equation as integration of minus infinity to plus infinity mod of h of t into e power of minus st dt. As we know the stability condition, integration of minus infinity to plus infinity h of t dt must be less than infinity. Therefore, real part of h must be equal to 0. Therefore, s must be equal to j omega. Now we see frequency domain condition for linear time invariant systems. For a discrete time system, the condition for stability is that the region of convergence of the Z transform includes the unit circle. When the system is casual, the ROC is the open region outside a circle whose radius is the magnitude of the pole with the largest magnitude. Therefore, all poles of the system must be inside the unit circle in the Z plane for Beebo stability. In this slide, we see the mathematical stability condition that is derived from the time domain condition for a discrete time signal. Therefore, for a discrete time signal, we know that the stability condition as summation of mod of h of n from minus infinity to plus infinity must be less than infinity. This can be written as summation of mod of h of n into mod of e power of minus j omega n from minus infinity to plus infinity, and this can be written as summation of mod of h of n into r into e power of j omega minus n whole to the power of minus n from minus infinity to plus infinity. Therefore, we keeping the r into e power of j omega as z, we can say that finally the equation will be summation of mod of h of n into z to the power of minus n minus infinity to plus infinity. Here z is r into e power of j omega and r is the magnitude of z, which is the radius of the ROC, means region of convergence, which is equal to 1. Therefore, we can say that the region of convergence is within the circle, unit circle. By using this equation, we can find the stability condition for a discrete time signal. As we completed the stability part, let's go to the causality of digital systems. What is causality and how do we define it? Let us see causality. A causal system is the one in which the output y of n at time n depends only on the current input x of n at time n and its past input sample values such as x of n minus 1, x of n minus 2, x of n minus 3, etc. Here we can see the mathematical definition for a causal system. Definition 1. A system mapping x to y is said to be causal if and only if for any pair of input signal x1 of t, x2 of t and any choice of t0 such that x1 of t equal to x2 of t for all t less than t0 and the corresponding outputs satisfy y1 of t is equal to y2 of t for all t less than t0. Definition 2. Suppose h of t is the impulse response of any system h described by a linear constant coefficient differential equation. The system h is said to be causal if and only if h of t equal to 0 for all t less than 0. Otherwise, it is a non-causal system. Here are some examples of causal system. The first one is memoryless system. The equation y of t is equal to 1 minus x of t into cos omega t is an example of memoryless system. And second one is autoregressive filter. This is a filter with the equation y of t is equal to integration of 0 to infinity x of t minus tau into e power of minus beta tau t tau. These are the examples of causal systems. Please do like, comment and subscribe to DSP NATAP.